Perfect. So yesterday we started looking at inverse trig, and we looked at how you type it in on the calculator. You're pressing second using the button. We looked at two different abbreviations. You can either write sine with the -1, or does anyone remember the other abbreviation? Yep.
It's arc.
Yeah, arc sine or arc cosine or arc tangent. Yep. And then we also looked at how to use that table if the answer is a multiple of 30 or 45 to look up the answer using that. So we learned yesterday that if you take the inverse sine of the sine, they cancel each other out. And the answer that you get right here is whatever you plugged in to start with. All right? So the first thing I want to make sure it's clear here is there's no multiplication happening there. This is read as the inverse sine of the sine of x. It's kind of like if I type something in on the calculator like, let's say I do the square root of 7. There's no multiplication at all there. That's just the square root of the number 7. 7 is just the thing I'm plugging into the square root function. Okay? In this case, sine is this whole thing is being plugged into that. Okay? So you'd essentially do something like this. The inverse sine, and now of, and now you fill in something there. Okay? I'm going to fill in sine. I just want one sine, not two. Like that. Okay? So that's the inverse sine of the sine of x. Now I want to pick a number for x and try it. Okay? Let's plug in like 8. Okay, just doesn't matter. And I'm going to do it in degrees. Okay. When I hit enter, I get back the same thing that I started with because the inverse sine and the regular sine cancel each other out. Okay. What if I did the inverse sine of the sine of 14.6? When I hit enter, what do you think I'll get?
14.6.
Right, I get 14.6. It's the same thing if I said to you, I want you to take the square root of, I don't know, 8 squared. Well, square and square root cancel each other out, so you get back exactly what you started with. Okay, we're doing the same thing. Let's try this one. The inverse sine of the sine of 92. Okay, based on the the first two that I did, what do you think I should get?
92.
Okay, you'd think I would get 92, right? Because we saw that's what happens with these first two, but we don't quite get 92. We get 88. So we didn't get back the same thing. Does anybody remember yesterday when we talked about inverse sine? I said that you're always going to get an answer between two numbers. That number is not between the two numbers that it should be. Does anybody remember what the two numbers were?
-90 and 90.
Right, -90 to 90. So this formula works as long as you plug in a number that follows what we set up yesterday. It has to be between -90 and 90. Or, if you're in radians, that's -pi/2 to +pi/2. So inverse sine of the sine of -47. Is -47 between -90 and 90?
Yeah.
Yep, that one's going to work fine. It's only if you go past -90 and +90, it doesn't work. So that formula 2a, that's just what your book calls the formula. That's all. It's not really important. The formula is important, but the 2a isn't. Okay, formula 2b. What's the difference? If you look quickly, they look the same. But yeah, what's flipped? What do you mean?
The inverse sine and the inverse.
Right.
Taking the sine of the inverse sine.
Right. This time we're taking the sine of the inverse sine. So what's the difference? Well, it's kind of like me saying to take 8 squared and then take the square root of it, or take the square root of 8 and square it. Those are different order of operations. These come out the same. If you take the square root of 8 and square it, or you take 8 squared and square root it, they come out the same. With inverse trig, though, we got to be careful. They do cancel each other out if you take the sine of the inverse sine, but x has to be between -1 and +1. Now, we haven't talked a lot about why it would have to be between -1 and +1, but it has something to do with the picture of sine, which we did look at yesterday. Okay. Here's the picture of what sine looks like. If you look at it, what's the highest that it looks like it ever goes? 1. Okay, that's the highest. And how about the lowest? -1. So the reason why this has to be between 1 and -1 has to do with this picture only going between -1 and 1. Okay? So let's try it. Let's take the sine of the inverse sine of 0.78. All right. Is 0.78 between -1 and 1? Yep. So when I hit enter, what do you think I'll get? Right. These two things cancel each other out, and I get back what I started with. Right? If I do the sine of the inverse sine of -0.64, what do you think I'll get when I hit enter this time? I'll get -0.64. Yep. Now, let's try one that's not. The sine of the inverse sine of 1.6. Okay, is 1.6 between -1 and 1? No. So let me show this to you visually. I'm going to put 1.6 in. Where does that red line cross the blue wave? It doesn't. Okay? When I type this question in, that's what I'm asking visually. I'm asking where do those cross? And they never do. So when you try to do a problem that doesn't have an answer, that's what's going to happen. So in this case, if you pick a number that's not between -1 and 1, you don't even get something that is a number back. Okay? You get an error because it's impossible to do. Okay? Any question on that? All right, so those are our two formulas for sine. Now we'll look at the two for cosine and then the two for tangent. Actually, am I going to do, all right, I'll do some examples first and then we'll do cosine. All right, so let's try this one. So the answer here is yes or no. Right? Is the inverse sine of the sine of pi over 8 equal to pi over 8? So the first thing we want to figure out is which formula are we looking at? Is that one formula 2a or is it more like 2b? Right, that's 2a because the inverse is on the outside and regular sine is on the inside. Yeah. So what is the argument supposed to be between in formula 2a? Okay, -90 to 90 if you're in what unit? Degrees. But we don't have a degree symbol on that. So what are we supposed to be between?
-pi/2, pi/2.
Right. We're supposed to be between -pi/2 and pi/2. So think of those two spots on a number line. We got to figure out where pi/8 is. If pi/8 is inside here, we're good. If pi/8 is over here or over here, then that's not good. Okay, we got to be in the green section. So how does pi/8 is a positive number? Okay, so is pi/2. So we don't have to think about the negative part. How does pi divided by 8 compare to pi divided by 2? Yep. Pi divided by 8 is a lot smaller, but is it still positive? Yeah, it's still positive. So if 0 is like right in the middle, pi/8 might be like somewhere right about there. The point is, it's in the green section. So if we do this out, would we get the answer back that we started with? Yes. Yep. So that would work fine. Right? Let's look at this one. The inverse sine of the sine of 3 pi over 2. Okay. First of all, is that the same type of problem as the last one, or is it different? It's the same type, right? Inverse on the outside, regular on the inside. Okay. 3 pi over 2. Okay. What kind of number is that? Positive or negative? Positive. And how does 3 pi over 2 compare to pi over 2? It's 3 times as large. It's triple pi over 2. So if you were to find where that is it going to be in the left, the middle, or on the right section? Yeah, it's going to be on the right section, like way over here. It's triple pi over 2. So it's not in the green section. So if I type that in, will I get back the answer I started with? No, it's too big. Whenever you do inverse sine, you will always get an answer between negative pi over 2 and positive pi over 2. You will never get an answer that big. Okay, so that one's done. All right, let's try this one. What's different about that one? Yeah, this one's flipped, right? The inverse is on the inside. So go back up to your formula. What is that supposed to be between when the inverse is on the inside? It's supposed to be between negative 1 and 1. We're at 1.5. So if I type that in, will these cancel out and give me back what I type in? No. That's the one where you're going to get an error. It's not that it gives you a different number back. It won't work at all. So that's no. All right. And how about this one? Same setup as the last one. Inverse is on the inside, and it's 0.6. Will that one work? Yeah, because you're supposed to be between negative 1 and 1, so that's fine. Okay, so that's one way I could ask this question. Is, and then I give you something, and you answer yes or no. Now, if I write the question like this, simplify, and I write sine of the inverse sine of 0.6. Don't put yes in that box. The answer is not yes. Right? Simplify means you got to actually do the problem out and tell me what the answer would be. So if I asked you to simplify that, what would it come out to? 0.6. Yeah. Not yes. Okay. So don't write yes if it's not a yes or no question. Any question on that one? Just a different way to ask the same thing. All right. Okay, let's look at cosine. Okay, so inverse cosine and regular cosine do cancel each other out. And what you get back is exactly what you typed in if you started with an angle between two numbers. Does anyone remember from yesterday what the angle had to be between when we were dealing with cosine? Yep. 0 to 180. Yep. So if you type in a number between 0 and 180, these will cancel, and you'll get back whatever you typed in. If you type in a number not between 0 and 180, you will get an answer back. It will be a number. It just won't be the number you started with. All right. And then when we switch it, put the inverse, take the cosine of, remember that's not multiply, it's the cosine of the inverse cosine. Just like the square root of 8 squared. You don't say square root times 8 squared. There's no times there. Now, for this one, that's where I showed you guys the picture and asked you how high and low the graph went. So let me graph cosine. I'm going to graph it on the same screen as sine. Okay, so it's doing, that's sine again, and you're going to see cosine in red. How high and low does it look like the red graph goes?
The same.
It's the same, right? Cosine and sine are very similar. It's just like they're shifted a little bit. But because it's exactly the same high point and low point, this formula has exactly the same numbers as formula 2b. All right, so let's try a couple examples of those. Let's start with that one. Okay. Is the cosine of the inverse cosine of 0.95 going to come out to 0.95? So first thing, is that formula 4a or 4b?
4B.
Yeah, it's 4b because the inverse is on the inside. Look at the restriction. Does that number fall between the two? Yeah. So the answer here would be yes. Yep. Okay, and the last one is the inverse cosine of the cosine of 210 going to cancel out and give you 210? No. Okay. Inverse is on the outside. You're supposed to be between 0 and 180. Okay. You're at 210. Inverse cosine will never equal an answer of 210. It's beyond what we said yesterday. Okay, so the answer there is no. Okay, so any question on when the cosine and the inverse cosine cancel each other out? So the last one we have is what function do we have left?
Tangent.
The tangent. Yep. Okay. So if you take the inverse tangent of the tangent of something, those two things will cancel out, and you'll get back exactly what you started with. If you started with something between, and what did we say for tangent? Yesterday we have to be between.
Negative 90, 90, but it can't be. Can't
Right.
be 90 or negative.
Can't be negative 90 or 90. That's why I do not have the equal to's under those. If you look back at formula 2a, I had the equal to's. Okay. This one does not. So we have to be strictly between negative 90 and 90. Or if you're doing radians, negative pi over 2 to pi over 2. Now, when we switch it, put the inverse on the inside. Something a little different happens. So to figure out what we have to be between here, for the B version of every formula, I've been graphing it and asking you how high and low it goes. Well, let's do the same thing. Let me graph tangent, put it in black, and I want you to tell me how high and low the tangent goes. All right, so based on that picture, does anybody have a thought how high and low tangent goes? Yep.
Infinite.
Yep.
Infinite.
Yeah, it goes up forever and it goes down forever. So in other words, that formula always works. Right? Doesn't matter what you type in. The tangent of the inverse tangent of 45.24. I just made that up. You're always going to get the same thing back. Tangent of the inverse tangent of 128.47. 128.47. If you go big enough, it might start to do some rounding on the calculator. I don't know. Let's see. Yeah, so you can see it's starting to do a little bit of rounding. I typed in 98,754.14, and I got 98,754.1399. It's because of the way the calculator is doing rounding. But technically, that is not what you get. Okay. It is 0.14. All right, any questions on that? So that's how I would kind of know if you know what you're really doing, because if you type that in on a calculator and you write that answer down, that would be wrong. I know you're just writing what you saw on the screen. They do cancel each other out, and you get back exactly the same thing. It's just the calculator is limited with how much accuracy it can do, and that must be beyond what the tangent and inverse tangent function can handle for accuracy. All right, so that's those formulas. And now I'll just ask you a question. The tangent of the inverse tangent of 30.4, will that come out to 30.4? Yes, because that's formula 6b. That always will work. And if you actually tried that, I think 30 is small enough that the calculator wouldn't have any accuracy issue. You would get 30.4. Yeah, because I did one even bigger. I did 45 and it worked. But when you start to get into like tens of thousands, the calculator does a little bit of rounding. Just for the heck of it, let's see. Excuse me, I try it on this calculator. What would happen? Okay, type in the same thing I did on the graphic one. Okay, so we had the, I don't know if I can do it the same way, the tangent. Yeah, this calculator, it works like the ones I like. You guys use like scientific ones you've used all through math. You type it in the order you see it. This calculator is backwards, so I have to type in everything in reverse, which makes it a little more complex. So I want the inverse tangent of that. So I get that. It's already doing some rounding. It should be, yeah, well, we'll see what happens. And then I'll take the tangent of that, if I can. Okay, that one actually gave me back the same thing I typed in, 98,754.14. So clearly these calculators are doing it, however they're doing what they're doing it a little differently. Right? This one's not doing as much rounding where the graphing calculator is. That's okay. All right, so any questions on that? All right, so that finishes up 3.1. So the first part of the homework will be some basically yes or no questions using those formulas. All right, let's look at 4.1. All right, so 4.1 is on what you call right triangle trig. You can also call it trigonometry with acute angles. I refer to it as right triangle trig. So first of all, because we're doing right triangle trig, it would be important to make sure we know what a right triangle is. And can anybody tell me what makes a triangle a right triangle? Yeah?
It has a right angle in it.
Okay, and what's a right angle?
90 degrees.
Right. So any triangle that has a 90-degree angle in it means it's a right triangle. When you have a 90-degree angle, that gives us some special names for the sides. What do we call the side, the longest side, across from the 90?
The hypotenuse.
It's the hypotenuse. And then the two other sides that are shorter, we call the legs. Yep. And there's certain letters we normally use when we name the sides. We'll talk about those in a minute. Okay, but here's a diagram of a right triangle. When we're solving a word problem and we have to make our own diagram, it doesn't matter which way you make the triangle face. If you're doing a right triangle problem and you want to face it that way, or you want to face it that way, it doesn't really matter. The point is every problem this week is going to have to do with a right triangle. All right. How about an acute angle? What's the definition of an acute angle? Yeah?
Angle smaller than 90 degrees.
Okay, smaller than 90, but it also has to be something else. We talked about other kinds of angles when we did like unit circle that would be smaller than 90, but they would not be acute. Think of, there's one other condition it has to meet. It has to be smaller than 90, but it also has to be, yep.
Bigger than negative 90.
It has to be bigger than something, but not negative 90. Yep.
Bigger than 0.
Has to be bigger than 0. You can't have a negative angle being acute. So like negative 10. That's not an acute angle. So less than 90, but greater than 0. It can't be exactly 0, because if your angle is 0, then you don't have an angle. And it can't be 0, and it can't be exactly 90, because then it would be a right angle. It has to be between 0 and 90 to be acute. All right. One theorem that we're going to use when we're dealing with right triangles is the Pythagorean theorem. And this theorem is all about sides. It has nothing to do with angles. Okay? If we want to figure out something involving angles, that's going to be inverse trig. If we want to do something with sides, this is one of the things we can use. And what is the Pythagorean theorem? Anyone explain to me what it is? Yeah.
A squared plus b squared equals c squared.
Okay, now can you explain, because just looking at my picture, I don't have any of these labeled as A, B, and C. What are A, B, and C?
The two legs are A and B, and the hypotenuse is C.
Right, yep. So the idea of the Pythagorean theorem, whether you call the sides A, B, C, or X, Y, Z, whatever you call them, if you take each leg and square them separately and add them together, that's going to be equal to the hypotenuse squared. Not a very hard formula to prove y at all. Right? Not something that I normally go through in this class, but when I teach it in pre-cal, we go through the proof y, and it basically has to do with drawing a square and some triangles inside the square. The diagram kind of looks something like this. You end up finding the area of this square inside here, and it proves that formula. Okay. It's just not something we're gonna go through. So a squared plus b squared equals c squared. Remember that this formula only works on a right triangle. So when we start getting into triangles that look like this, that is not a triangle you can use Pythagorean theorem on. It doesn't work. Okay. What does work, well, we'll talk about that when we get to it. All right, so what we're going to do is we're going to look at writing down the 6 trig functions, just like we've done before: sine, cosine, tangent, cosecant, secant, cotangent. But we're not going to define them using a unit circle. Okay, we did the unit circle, it was last week, okay, before vacation. So sine was y, cosine was x, tangent was y over x. We're going to define them today using some different terms: opposite, adjacent, and hypotenuse. We're using different words to define the trig functions, but it really is exactly the same idea as the unit circle. There's no difference. Okay. Just a different way to think about it. So before I can define them using those words, I just have to explain what those words mean. Okay. Okay. First of all, opposite and adjacent are kind of like the words left and right. There is no, like in this room, there is no standard wall that you could label left, because left is relative to the way you face it. Right? So for me, left is the door. For you, left is the windows. It's relative to you. Same with opposite. Okay, what wall is opposite me? The back wall. Okay, what wall is opposite you? The front wall. Okay, opposite is what's across from you. So again, it's relative to which way you're facing. So let's look at that in a triangle. The way that you know which way you are facing in a triangle is they will mark one of the angles like that with a Greek letter, and they will say something like from theta, which side is opposite. In this case, that's opposite, and that side would be adjacent. Adjacent, if you look up what it means, adjacent means something is next to you. So adjacent is right next to theta. Now, you might say, well, this side over here is also adjacent to theta. It is, but this side already has a name because it's across from the 90. That's the hypotenuse. So adjacent is the one that's right next to your angle. That's not the hypotenuse. Okay. Now, if you draw the same triangle, and let's change your reference point. Okay, so now let's do everything from the perspective of the angle up here. So it's kind of like now you're facing a different direction. What angle is opposite theta now? The bottom. Yep. And what angle is adjacent to theta? The left side. Yep. The one thing that doesn't change, no matter where your perspective is from in the triangle, is hypotenuse. I guess in this room, that would be like up. Whether I face this way, up is the ceiling. If I face this way, up is still the ceiling. Doesn't matter which way I face. So hypotenuse does not change, ever. It's always across from the 90. So any questions on the terms opposite and adjacent? Okay, if you want the definition spelled out, opposite is the side in the triangle that is not part of the angle at all. So if I had a triangle, actually I got one right over there. If I were to erase this side, it had no effect on that angle at all. Opposite is the side that's farthest away, and it is not part of the angle. Adjacent is the side in the triangle that is right next to the angle. It actually forms one of the sides. So in that diagram, if I erase the adjacent side, I don't have an angle anymore. I just lost one of my sides that was making the angle, that was forming the angle. Okay. So adjacent is the side next to the angle, but not the hypotenuse. So that's how you can describe it if you want to think about it in words. Any questions on that? All right, so now let's define the 6 trig functions using the words opposite, adjacent, and hypotenuse. Okay, and here are the first 3. So sine. Okay, so first of all, they're all fractions. Okay, all the definitions are fractions, and they're fractions of the length of one side divided by the length of the other side. And the reason that we need 6 different trig functions is because if you look at the 3 sides of that triangle, you have a red, a blue, and a black. There are 6 different ways that you can divide those 3 sides. You can divide red over blue, blue over red. There's 2. Blue over black, black over blue. There's 2 more. And then black over red and red over black. Those are the 6 different ways you can pick the 2 sides and divide them. So sine is the opposite divided by the hypotenuse. Okay. The cosine is the adjacent divided by the hypotenuse. And the tangent is the opposite over the adjacent. Now there's a way that some people use to try to remember those. It's like it's a word, like an abbreviation, like PEMDAS, but it's not PEMDAS. Does anybody know the word I'm thinking of to try to remember those? Yeah? Yep, Sakatoa. So can you tell me what that means? Yeah, sine is opposite over hypotenuse.
And then cos is adjacent over hypotenuse.
So yeah, the ka part in Sakatoa is adjacent over hypotenuse for cosine. Yep.
Just say that.
Yep. And then tangent is opposite over adjacent. Sa, ka, to. So those, you can use that to help you kind of remember the trig functions. One year when I asked the same question, is there a way you can remember the trig functions? Somebody said to me, Sacagawea. She's not going to help, not with this. Saccatello, not Sacagawea. It's close, not quite. All right. And then we got the other three. So we got the cosecant, the secant, and the cotangent. And if you know the three on the left, you automatically know on the three on the right, because what's the connection between each one of them?
The opposite.
Like the negative of it?
Or flip.
Flip, the reciprocal, yeah. So cosecant is hypotenuse over opposite. What would the secant be?
Minus over adjacent.
Take the hypotenuse, divide by the adjacent, and the cotangent?
Adjacent over opposite.
Adjacent over opposite. Now, let's just make up some numbers and see what happens. Let's say I was doing, it doesn't matter, let's do the sine. And I was doing the opposite divided by the hypotenuse. Well, let's say the opposite was 4 feet. And let's say the hypotenuse was 5 feet. The opposite is 4 feet, the hypotenuse is 5 feet. When I divide these two, what's going to cancel out?
Feet.
Feet. So the length unit is gone. That's why when we write the answers to any of these questions, we don't have to put any label on the answer, because the label that's in the top is the same that's the label that's in the bottom, and that means it's gone. What you're left with is a pure number with no label. That's all it is. It's just a number. It's like if I said, what's the ratio of boys to girls in a class? When you get that ratio, if it's like, 2 to 3, that's the ratio, there's no label on it. It's just 2 to 3. Just a number, because if you have like the same units, they cancel out. So same idea here. The units cancel out. It's just the number 4/5. All right. So now let's see if we can use those formulas to find the 6 trig functions of theta. So you know your perspective. Everything that you do in this problem is from the perspective of that angle that I just circled. All right, now we could do some of the trig functions the way that this is set up. We could do 2 of them, but we're missing a piece of information to do the other 4. What side are we missing? Yep.
The hypotenuse.
Yeah, we're missing the hypotenuse. Well, hypotenuse is in 4 of them. If you don't find that, you're not going to be able to do those 4. You could only do the bottom 2. So how are we going to figure out the hypotenuse as the first step in this problem? Yeah.
3 squared plus 4 squared equals c squared.
Okay, so what are you doing there? Yeah, we're going to do the Pythagorean theorem to find, in this case, the hypotenuse. And exactly what Ileana said. 3 squared plus 4 squared equals c squared. Okay, 3 squared is going to give me how much? 9. And then 4 squared?
16.
And what's 9 plus 16? 25. And now to get rid of the exponent of 2, what do we have to do on both sides?
Squared.
Yep, take the square root. And when we take the square root on both sides, this is kind of like sine and inverse sine. This is square root and square. They cancel out. And what are we left with for c? 5. Okay. If we were left with a square root, that's fine. We would leave it as a square root. And if we get a square root, 2 things. 1, we have to make sure it's always reduced. 2, we can't leave it in the bottom of a fraction. Okay. So if you end up with, say you ended up with a problem like this, you don't want to leave a final answer with, say, the hypotenuse was square root of 3. Don't leave that in the bottom. We have to fix it. Just like we did with unit circle trig. Multiply top and bottom by square root of 3. Okay. That's not part of this problem. That's just something I made up to show you what happens if you're left with a square root. Okay, but this one we don't have a square root, so that's going to make it a little nicer. All right, let's see if we can do all 6 trig functions. Let's start with sine. What is the definition for sine? Yep.
Opposite over hypotenuse.
Okay, opposite over hypotenuse. And using this problem, what would the opposite over the hypotenuse be?
4 over 5.
Yep, 4 over 5. And that's it. Okay. So if I ask you on a test, what is the sine of theta? You would just write 4/5. What you're not doing in this problem is solving for the angle. We're not solving for the angle today. That'll be tomorrow. But you should already know how to do it. If we wanted to solve for that angle, you'd have to get rid of the sine. And you should know what would cancel out sine at this point. What would cancel out sine? Arc sine. Yep, or inverse sine. So if you wanted to find this angle, you would use inverse sine. That's why I keep saying inverse trig finds angle. But that'll be tomorrow. Okay. How about the cosine? What's my formula for cosine? Yep, just
Adjacent over hypotenuse.
adjacent over hypotenuse, which in this case is
3 over 5.
3 over 5. And my formula for tangent. What's that one?
Opposite over adjacent.
Opposite over adjacent. So in this one we would have
4 over 3.
4 over 3. And that's one we could have done without finding the hypotenuse. Okay, so if all I asked you about was the tangent in this problem, you don't need Pythagorean theorem. Okay, but I asked for all 6. All right, so we got all the 3 on the left. What are we going to do with each one of them to get the 3 on the right? Yep, flip them. So cosecant, 5/4, secant, 5/3, cotangent, 3/4. Okay, when you are writing the trig functions, like we just did, we will always leave the answer as a fraction. Okay. Unless it came out to an integer, that's fine. But I don't think, most of them are not going to come out to nice numbers. So like you'd never write 0.8 or 0.6. Just leave it as a fraction. Any questions on that one? All right. So that's finding the 6 trig functions of an angle. All right. Next, we'll talk about what's called complementary angles. Usually you study this with supplementary, so some people mix them up. Does anybody remember what complementary means? Yep.
Given.
It's what?
Given.
Well, to know if 2 angles are complementary, yeah, I would have to give you 2 angles, but you would have to check something about the 2 angles that I give you to know if they are complementary. But yeah, they would be given to you. Yeah.
If they add up to 90.
They have to add up to 90. Yeah. So 2 angles that add up to exactly 90 are complementary. Okay. Let's look at this. We don't normally label the angles 1 and 2. We usually use Greek letters, but for now, I just labeled them 1 and 2. If I were to add 1, 2, and the right angle together, what do we know about all the angles inside a triangle when you add them up?
180.
They add up to 180, yes. So what does that tell you about angles 1 and 2? They add up to what?
They have to 90.
Right, angles 1 and 2 have to add up to 90 because that's 90. So these 2 also have to add up to 90 because they all have to make 180. So angles 1 and 2 have to add up to 90. What does that mean about angles 1 and 2?
They're both 45. Or
No, you could have one that's like 80 and one that's 10. You could have something like that. but they both have to add up to 90, so what does that mean about them?
They're acute.
They are acute, yep, they both have to be acute, and something else. They add up to 90, right? They're complementary, yeah. So the two acute angles in a right triangle are always complementary. Because that one and that one always have to add up to 90. Okay, so that's important to remember. Two acute angles in a right triangle are always complementary. Just another way of saying they add up to 90. So any questions on what it means to be complementary? All right. So the next thing I want to look at is, let's go back to these functions. Actually, you can look at them right here. Just looking at the names in blue. Okay. The way that they're paired up with each other right now, going left to right, those are called reciprocal functions. Reciprocal means if you flip one, you get the other. Well, there's another way you can pair them up, and that's like this. Those two, and those two end up being the same. If you pronounce what's in each of the red boxes together, sine, cosine, secant, cosecant, tangent, cotangent, there's a pattern there. Does anyone see the pattern between these two, those two, and those two? Each box has the same pattern to how I group them. Yeah?
The co in front of the previous one.
Right, putting co in front of the function. So you have tangent. What do you get if you put co in front of it? Cotangent. Secant, co-secant. Sine, cosine. When you put co in front of a trig function, that is called the cofunction. Every function has a cofunction. Now, for cosine, you wouldn't put co in front of it again and say cocosine. No. The cofunction of cosine is just sine. You take the co away. So whether you take the co away or you put the co in front of it, that's called the cofunction. And there are the three pairs of cofunctions. Same way I just grouped them in the other page on the red box. Okay, so we've paired these up as reciprocal functions before, flipping one to get the other. Now we're pairing them as cofunctions. It's a little different. Except tangent and cotangent, yes, those are reciprocal functions and cofunctions. They're both. But they're the only pair that are both. Any questions on those three pairs of cofunctions? Now we're going to put these two ideas together, cofunctions and complementary, and I'm going to show you something that happens. All right, so let's look at this diagram. That is how you normally draw, or how you label a generic right triangle. You label the sides as A, B, and C, and you always use Greek letters for the angles. So we've talked about why we use Greek letters. Some books use capital letters for angles and lowercase letters for sides. That can be confusing, especially like a C. Capital C and lowercase c look the same, so you can run into some things happening. But if you stick with English letters, A, B, and C, and Greek letters, alpha and beta, then there'll never be any confusion about is alpha an angle or a side? It's an angle. The placement is important. Okay. To keep everything straight, we usually put alpha across from A, first letter in the Greek alphabet across from the first letter in the English, and beta across from B. Second letter, second letter. Alpha goes with A, beta goes opposite B. Now, which way you face the triangle, that I don't care about. If you want to face it that way, that's fine. Put A and B wherever you want. That's not the hypotenuse. If you face it that way, that's fine. A is at the bottom, alpha is at the top, and beta would be in the lower left. That's the same triangle. It's just like a rotation and kind of a mirror image of it. But it's the same thing. All right, so now let's try finding a couple trig factors. Let's do the sine of alpha. Okay, I just picked a trig function, I just picked an angle. So alpha is your reference point. Everything is from alpha for this problem. Sine is opposite over hypotenuse. What's opposite and what's hypotenuse from alpha in this case?
A.
Yeah. Go ahead, Jim.
A is opposite and C is the hypotenuse.
Yeah. So A is opposite and C is the hypotenuse. That's it. That's the answer. We don't know what A and C are, but we know that the sine of alpha would be A divided by C. Now, I'm going to make up another problem, but I'm going to make up something very specific. What is the cofunction of sine?
Cosine.
Cosine. So I'm going to use that function, the cofunction. And what angle is complementary to alpha? So A is a side. Beta. Okay. So I did two things to make up that new question. I found the cofunction of that, and I found the complement of that. Now let's try that one. What's our formula for cosine? Adjacent over hypotenuse. Okay, so from beta, what side is adjacent? A. And what side is the hypotenuse? C. And what do you notice? They came out the same. So the sine of alpha and the cosine of beta are exactly the same. What number does it come out to? Well, I don't know that because it's just variables. But they do come out the same. All right, let's try one more. Let's pick another trig function. Let's do tangent of alpha. All right, tangent is opposite over adjacent. What's opposite over adjacent from alpha?
A and B.
So it would be
A over B.
A over B. Yep. Now, let's make up another problem, but let's do it like we did the first one. Cofunction, complement. What's the cofunction of tangent? Cotangent. And what's the complement of alpha?
Beta.
Beta. Okay. Cotangent is adjacent over opposite. What side is adjacent to beta?
A.
A. And what side is opposite? Beta. B. Came out the same again. And the fact that it's coming out the same, it's not random. That's going to keep happening as long as you're dealing with cofunctions and complementary angles. And that's called the complementary angle theorem. Very simply, it says that if you have cofunctions and you have angles that are complementary, when you solve each of those problems, they will come out exactly the same. So let's see if we can figure out what these would be the same as. To figure out something that's the same as it, find the cofunction, and then find the complement. So this isn't going to give you the answer for the sine of 30. What it's going to do is give you another way to figure it out. That's what it does. So start with sine. Okay. What's your cofunction? Cosine. And what's the complement of 30? 60. The sine of 30 and the cosine of 60 come out exactly the same. And I can show you if I just type it in. I'm not going to type them all in, but I'll just do the first one. They come out exactly the same. Now, the fact they come out the same, how does that help you do anything? That'll be the last thing I show you. Okay. Tangent of 15. What would that be the same as based on the complementary angle theorem?
75. That's, yeah.
Yep. Cotangent of 75. Yep. Those two would be the same. So what is the tangent of 15? Well, that I don't know. I'd have to do it out. But it comes out the same as the cotangent of 75. How about the secant of 40? That would be the same as, yep.
Cosecant 50.
Yep, cosecant 50. All right, so what good does that do? Why does it help to write something in a different way? It still doesn't give you the answer, but it will if you're doing a certain kind of problem. I want to do this. The sine of 15 divided by the cosine of 75. And I'm actually not as interested in what even that comes out to. I'd be more interested in why you got what you got. So I would probably ask you to type in why you got what you got. What do we know about sine and cosine? There's a relationship between them. They're co-functions. Yep. What do we know about 15 and 75 degrees?
Complementary.
They're complementary. They add up to 90. So these are co-functions. These are complementary angles. So we know that what's in the blue box and what's in the green box, how do they compare to each other? They're exactly the same thing. So you are dividing two things that are the same, which would give you what? 1. So that's where this theorem helps you figure something out. It's a very specific situation. If this was 14 degrees and that was 75, then no, it doesn't work. These have to be co-functions, and those have to add to 90. And if you divide them, you'll get 1 because they're the same. Right? Now, how about with multiplication? Instead of dividing two things that are the same, if you multiply two things that are the same, do you always get a number like 1? Yeah, Shane, what do you think?
No.
No. If you multiply two things that are the same, you don't always get the same thing. 3 times 3 is not the same as 4 times 4. 3 divided by 3 and 4 divided by 4, those are the same. But it doesn't work with multiplication. So this trick will help you with division, and it will help you with one other operation. It's not multiplication. Anybody know what other operation it would help you with? It would help you with subtraction. Yep. Okay. We've got tangent, cotangent, 12 and 78. Tangent and cotangent are co-functions. 12 and 78 are complementary. So we have co-functions of complementary angles, which means the two expressions are equal. So what would you get when you subtract two things that are equal? 0. Yep. Now, if you add two things that are equal, do you get the same thing? No. Like 5 plus 5 is not the same as 4 plus 4. Okay. But 5 minus 5 and 4 minus 4, those are the same. Okay. So it works with subtraction. It doesn't do anything for addition. And that's called the complementary angle theorem. Any questions on that? All right, so that finishes 3.1 and then the first half of 4.1. So the top part of the homework on 187, those are yes or no type questions. And page 255, that's what we just did right now. Okay, that's the right triangle, Socotoa stuff. Okay, so we'll go over that tomorrow. We'll finish it up. And then Thursday, as long as we finish tomorrow, Thursday should be a review day.